Guys, if you look at this chapter here, this is basically simple kinetic molecular matter, right? Which once again talks about the solid, liquid, and gas states, which I don't think I want to go through too much, because everyone should know this by now. The only thing that I want to talk about is something relatively new, which is known as absolute zero. In school, you all learn about absolute zero already, right? Anyone recall anything about absolute zero, by the way? Maybe starting with Eason. Hey, yeah, Eason. What do you know about absolute zero?
It's like a theoretical temperature that we haven't reached yet.
Okay, that's correct. It's a theoretical temperature that we actually cannot reach, but it's basically the lowest possible temperature achievable in the universe, right? We haven't reached it yet. In this case here, absolute zero is literally 0 Kelvin. Okay. This 0 Kelvin is the lowest possible, in your exam, they'll ask you this, the lowest possible temperature achievable in the universe. It is so low that the particles seemingly stop vibrating. You know how solid particles, they still vibrate in fixed position, right? The absolute zero temperature is so low that it seemingly stops vibrating, but there's still some vibration because we cannot fully stop the vibration, right? So in your exam, you need to be able to write this. Absolute zero is the lowest possible temperature achieved in the universe. All motion has virtually stopped. Virtually only. There's still like very, very little vibration because there's still very, very little energy. Okay, everybody? Okay, so once you understand this, right, everything else kind of makes sense already. You just need to remember this number, lor. For absolute zero or Kelvin to degree Celsius, right, the key number that you're looking at is basically 273. I have a really dumb way to remember this, but maybe that might be a generation gap for you guys. Anyone here don't know who Mariah Carey is? You don't. Mariah Carey is the lady that actually sings the Christmas songs when you go to the shopping mall all the time. Yes, but anyway, yes, I know it's a generation gap because old, right? But anyways, uh 27th of March is her birthday. The lady that sings Christmas songs throughout the whole shopping mall all the time. 27th of March is her birthday, which is something dumb. And always the something dumb that is easier to remember. Okay. For those who don't, in case you don't know who I'm talking about, here, let me show you who Mariah Carey is. Most famously known for her Christmas songs. For sure, maybe no lah, maybe you guys don't know because that's literally a generation gap thing, right? But if you listen to any Christmas songs in the what's it called, the shopping malls, it's definitely her song. And once again, her birthday is on shit, where is it? 273, 27th of March. Remember, okay? Remember this dumb story and remember this dumb number because you will need it. Okay? So with this here, it's very straightforward, right? You see, at 0 degrees Celsius, right? I'm basically gonna you can ignore the 0.15, by the way. Just ignore the 0.15. I can basically at 0 degrees Celsius, I just plus 273, it becomes 273 Kelvin. Okay. At 100 degrees Celsius, I just need to plus 273 and I'll get 373 Kelvin. Okay. What if I have somewhere in the middle? Uh, what if I have, let's just say, guys, 300 Kelvin. How many degrees Celsius is that, Shane?
Uh, 27 degrees.
Good, it's 27 degrees Celsius. So you just play around with the 273 lah. It's not that hard lah, right? And obviously at 0 Kelvin, how much is that in degrees Celsius, Jolie? At 0 Kelvin, how many degrees Celsius is that?
273.
Just 273?
Okay.
Okay, degrees Celsius for bro. Oh, it's negative 273
Oh, oh.
Okay. It's negative 273. Hey, you guys need to know how to convert Kelvin into degrees Celsius and degrees Celsius into Kelvin. Because see, this is I think they're changing the syllabus again next year. But this is still there. So and this is relatively new. So they will actually include it if not in paper 4, for sure in paper 2. Okay, you need to know how to convert this. Right. So just remember the 273. Okay. Uh Anyone don't know what I'm talking about? Anyone need me to emphasize or repeat anything? Or want me to clarify any doubts? Good. Okay. Anyways, yeah, convert everything yourself and then copy everything down here. Make it quick.
Sure, the separation of particles for liquid is far.
Oh, that was a test. You pass. They are not far. They are actually touching each other, so they're actually close.
Well, I don't trust your notes anymore, Jer.
That's why you gotta question it, bro. Don't listen to anyone. Question. Don't just.
Yeah, I don't listen to your notes anymore. I read my own notes.
Wait. Hey, I'm human too, right? I also will make mistakes one. But it's good that you ask because logically speaking, liquid particles are already touching each other, right? How can they be far apart? Namo. That was a test. You pass. Everyone else. In fact, right? I think this mistake has been here for a very long time, eh? No one ever corrected me before. I want to mention one more thing in your exam, right? Since we're on this topic, right? I think the reason why no one questioned me is because they based their answer upon this diagram. Do you know that liquid particles, when you draw like this, you actually will get wrong? You need to draw the liquid particles randomly organized, but all actually touching each other. Right? Solid particles, it will be like nicely lattice arrangement, right? But liquid particles will be like random, right? And they are most certainly not far apart. Moving on, this next part here, which a lot of students give me a wrong answer, this one. It's in the first chapter in chemistry as well, guys. So let's imagine, right, today I have a closed container, right? And I have particles. Wait, everyone pay attention, right? Pay attention, right? Stop looking down, everyone pay attention. So if I have a closed container, I have gas particles, right? What happens is in a normal scenario, they'll just constantly collide against the walls slowly and taking their time, and then they'll change direction, right? And what happens when I start heating up the closed container? When I start heating up the closed container, I'm effectively supplying energy to the gas particles inside, right? Or molecules or whatever, right? And because of that, they gain kinetic energy and they collide against the walls more faster and more frequently. Okay? This is the reason why, right? Anytime you have a heated container, when you open it, you'll hear a pop sound. It's because the pressure is different. For those who own a thermal flask, which is most likely everyone, if you put hot water in it, right, after sealing it for a while, when you open it up, you hear the pop sound. Why? Because inside the thermal flask, your hot water, right, acts as the energy supplier to the air molecules above. And because of that, the air molecules gain energy, so they actually collide against the walls of the container more frequently. As they collide against the walls of the container more frequently, they actually generate a greater force per unit area, which will ultimately lead to a greater pressure inside the container. You know what's the common mistake that I see a lot of students answer me when they're dealing with this question? They'll tell me that the particles are colliding with itself or against each other. Guys, this is not a chemistry question, guys. Chemistry, when the gas particles collide with each other, they'll basically go through a chemical reaction, right? But this one has to do with pressure, guys. It has to do with pressure, and from here, what you should know is that a greater temperature is usually going to dictate a greater pressure, simply because the gas particles collide against the walls of the container more frequently. And because you collide against the walls of container more frequently, it generates greater force per unit area, ultimately increasing the pressure. These are the few keywords, guys. Increase collision rate, collide against the wall, increase force per unit area, ultimately increasing the pressure. And this comes out all the time in your paper 4. You need to know this. Next, we talk about Brownian movement, which is essentially the random zigzag motion of air particles in smoke, or smoke particles in air, either one. So let's imagine this, guys. Basically today, right, you blow like a puff of smoke into a glass container. Why would you guys be blowing a puff of smoke? Unless you're smoking underage. Anyways, let's assume that is the scenario, right? You blow a puff of smoke into a glass container and then you start shining a light onto it, right? As you shine a light onto it, then you're going to look through at the microscope. You'll notice that, right? Instead of what I've told you just now, right? I said that the particles will collide against the wall and then change direction, right? This will almost never be the case. Before they even reach the walls of the container, they start randomly moving in random zigzag motion already. Why? This is simply because, right, even before they reach the end of the container, right, maybe they'll collide with other particles here. Collide, change direction, collide, change direction, collide, change direction, collide, change direction, change direction, change direction, change direction, change, and so on, right? So because it randomly collides with other smoke particles, what happens is, right, you'll notice that it will constantly move in a random zigzag motion with random speeds. And that's your definition for Brownian movement, guys. Brownian movement states that the smoke particles will move in a random zigzag motion with random speeds. In your exam, if they ever ask you to name the characteristics of Brownian motion, you actually need to mention these two things. Quite commonly asked in your exam as well, but not so much anymore in the recent years. But it's still in your syllabus, so you need to know. Okay? Brownian movement, random zigzag motion with random speeds. Every time it collides, maybe after it collides with one particle, it moves, let's just say 10 meters per second. Then it collides with another particle, maybe it moves 8 meters per second. Then if they collide, it becomes 6, then collide again becomes 12, then collide again becomes 13, and so on. It's totally random. There's no pattern to it. Okay? That's why they call it random speed and random zigzag motion. You can't really predict the pattern. Okay? Guys, anyone has any questions for Brownian movement? Moving on to this next part here, right? Basically, you need to understand how does pressure and how does temperature and volume affects the pressure lah. Just now we already gave you the example, right? A higher temperature is going to give them more energy and thus is going to have a higher pressure in any closed container, right? From here, I need to know that pressure and temperature, they are directly proportional. However, pressure and volume are actually inversely proportional. By the way, in order for anything to be directly proportional, it must start from the origin and one straight line. A lot of students, they tell me that, oh, this one also one straight line upwards like this one. This one also directly proportional, which is not the case. In order for anything to be directly proportional, it must start from 0 and it must be one straight line upwards, okay? Whereas inversely proportional will be a curved line like this. Okay, pressure and volume are inversely proportional because if you think about it, right, you guys ever try to pop a balloon before? If you ever tried to pop a balloon before, right, imagine the balloon was this size and you start compressing it. You can literally feel the pressure building up as you compress the balloon, right? This is simply because with a smaller space, the same amount of air particles is occupying it, and thus it actually collides against the walls more frequently. Okay, a graphical representation will look something like this. Imagine a balloon that has exactly 8 particles here. Okay, with these 8 particles, right, in a normal scenario, it will just slowly collide against the walls, right? No problem. But as soon as you start compressing the balloon, the same amount of air particles occupy a much smaller space, and because of that, they will collide against the walls of the container more frequently, once again increasing the force per unit area, which will once again increase the pressure. Okay? You need to be able to explain this in your exam, which is very, very commonly asked in your exam. They'll ask you in terms of particle theory or something, or kinetic particle theory, Explain why pressure and volume is inversely proportional. You need to mention all these things. It's just basically saying it has a smaller space and it collides against the walls more frequently. Then you're good to go. Okay, guys? Frantically copy. I hope you all understand before you start copying. Anyways, the last thing I want to talk about is basically Boyle's law. Okay, Boyle's law is essentially saying that P1 V1 equals to P2 V2. Let's imagine, right? Let's imagine today I have like a swimming pool here, a very, very deep swimming pool. And then I let a gas bubble upwards here. Okay, I release a gas bubble at the bottom of the swimming pool. As it rises towards the top, first question I want to ask, Hayden, will the volume increase or decrease? Will the volume of the gas bubble increase or decrease as it rises towards the surface?
Decrease.
No, it will increase. Which leads to my next question. Ethan, how come the volume increases as it rises towards the surface? What's going on?
Actually, I go first, but
Okay, it's you.
Because the pressure decreases as it goes up.
Good. So basically at the bottom here, there is a lot of pressure acting on it, right? Due to your water, right? And at the top here, there's definitely much smaller pressure as you go upwards. Because of this, you can actually tell that a high pressure will have a low volume, whereas a low pressure will have a high volume. Okay, how do I use this Boyle's law? I can literally put in some fake numbers. Let's say, for example, this pressure here is, I don't know, let's say 100 Pascal, right? And the volume here is 5 meters cubed. Okay, let's say this volume increased to 20 meters cubed. How much do you think the pressure here will be? Jolie, can you tell me how much do you think the pressure here will be based on this formula?
Uh, um,
20?
what?
How much do you think the pressure will be?
Wait, hold on.
Huh?
Hold on, hold on.
Oh.
Uh, 25.
Good. The answer is going to be 25 by using this formula here, because this will be P1, this will be V1, this will be P2, and this will be V2 here. Oh, oops. Sorry, what? Right. So from here, you can once again see that high pressure, low volume, low pressure, high volume. Understand now, boys? You guys
Yes.
get the whole idea? Yeah?
Yes.
Good. Guys, please copy everything down.